Alright, so this is a slightly different video than normal. It's been a while since I've done one of these. I think the last one was like 2015 or so. But my son figured this out. It's probably already a well-established uh, math concept. But so anyways, he figured out this sequential prime. Um, I don't know if you call it an algorithm or what. And then in doing the rigorous proof for it, we found an improvement to the Bertrand-Chebyschev theorem. So here, I'll go through and explain it. So first we define odd numbers. M1 is going to be in some odd number, the form 2k plus 1. M2 is 2j plus 1. Uh, Basic definitions of odd numbers. And we're going to assume that M1 is greater than M2, and then M2 is greater than M1 plus 1 over 2. And I'm going to provide, I use some examples down here. And k and j are integers. And then we're going to let h be an integer such that it's m2 minus the mod of m1 with m2. H will always be an odd number. So we're going to go through and kind of demonstrate this. So let's say m1 is equal to 7. That means m1 plus 1 over 2 is equal to 4. 7 plus 1 is 8. 8 divided by 2 is 4. And m2 is going to be 5. So 7 is greater than 5 is greater than 4. So the mod of M1 with M2 is 7, 7 mod 5 is equal to 2. 7 divided by 5, you'll have a remainder of 2. Uh, so H is going to be 5 minus 2 is 3. So we're going to go through, this is going to be useful for further in the rigorous proof. Um, we can show that M1 plus 1 over 2 is is the same thing as m1 over 2 plus 1 half. We demonstrate that here. A lot of this should be very, very simple math, pretty given. Um, and let's see, the sum of two positive numbers is greater than either positive number. Again, very, very simple. 2 plus 3 is greater than 2 or 3. In this case, m1 over 1 plus 1 half is greater than m1 m1 over 2 plus 1 half is greater than m1 over 2. Um, and of course, that makes sense here. 7 halves plus 1 half is greater than 7 halves because it's 8 halves, which is greater than 7 halves. So just this is just going through the very basic rigorous part of it. Um, so using our given, and I'm always going to use an example here so we can visualize what's going on. We do a substitution. Um, so since we know that uh, let's see, 7 plus 1 over 2 is greater than 7 over 2. We can just straight substitute that. So if 5 is greater than this, then it also must be greater than this, right? So we do some algebraic manipulation. We're going to multiply both sides by 2. So it's going to be 2 times m2 is greater than m1. 2 times 5 is greater than 7. Um, we're going to, let's see, subtract 2m2 from both sides. So 10 minus 10 is greater than 7 minus 10. 0 is greater than negative 3. Subtracting 2m2 from both sides. There we go. Okay, so by the definition of modulo, because this m2 is greater than m1 over 2, then that means that n, the whatever multiple of m2, must be equal to 1, which, yeah, it makes sense. It's not going to be 7 minus 2 times 5 because you'll have negative 3. So the mod has to be, where it's 2, is relies off of n being equal to 1, where n is some integer. So m1, and again, covering basic stuff, m1 is equal to m2 plus m1 mod m2. 7 is equal to 5 plus 2. Um, all right, so let's see, odd numbers in integer of the form m is equal to 2j plus 1. We covered that in the previous slide. Um, let's see, m1 plus is equal to m2 plus m1 mod m2. And that's going to be greater than 0. 7 equals 5 plus 2. That's greater than 0. So we're going to do some algebraic manipulation real quick. Um, so let's see. So that means that 7 minus 2 is equal to 5. So M1 minus that mod is equal to M2. Remember, n is the multiple and n is equal to 1. So we're fine there. So now we're going to subtract the mod from each side. So we're going to have 5 minus 2. And now we're going to have 7 minus 2 minus 2. And it's going to be 7 minus 2 times 2. Kind of flying around me. All right, so um, then let's see, where did we go? Oh yeah, 5 minus 2, 3. Yeah, M2 minus M1 mod M2. Uh, yeah, let's see. Okay, and this is going to lead into the very next part of the proof. So in the end, that h that we talked about previously is going to be an odd number if those are primes. The only exception I think is going to be if the prime is 2, but we'll cover that. Um, so h must be prime because you're going to have m1 minus 2 times the mod. So let's see. We're going to do a proof by contradiction here to demonstrate it. Excuse me. Uh, so let's pretend that it's an even integer. We already kind of know that it's going to be odd, but just in case, let's do a proof by contradiction. H is, let's assume it's an even integer where it's 2 times a, where a is some integer. So 2a is equal to this mess that we did up here, yeah? Let's divide both sides by 2. A is equal to m1 over 2 minus that mod, that because it was twice the mod before. Um, so remember, m1 is equal to 2j plus 1. So we're going to substitute that in. So a is equal to 2j plus 1 over 2 minus the mod. And then we're going to separate it into two different fractions. A is equal to j plus 1/2 minus the mod. Now, since the sum of an integer and a non-integer is always a non-integer, we have a proof by contradiction. Therefore, h must be an odd number. Okay, so that gives us to where we can go next. So let's imagine some prime number, some largest prime number that we know. And we're going to create a set A of all the odd numbers, excluding 1, up to AI, such that AI is equal to that prime number, the plus 1 divided by 2. For our example, let's imagine the prime number is 7. Um, so that means our set, A1, A2, A3, AI, whatever, is going to be all the odd numbers, excluding 1, up to our P max. Uh, so let's see, or sorry, up to this right here. It's the P max plus 1 over 2. So our set A is just going to be 3 and 5, because remember, we're excluding evens and we're including the number 1. Next, let's create a set B of integers from 1 to AI. So the highest B max, is going to be equal to AI. So our set B, B1, B2, B3, B max, is 1, 2, 3, 4, 5. So we have some numbers that are missing, right? So now let's create C. Now this is where the previous proof came in, or is going to come in. So for our set C, for each CI is going to be AI minus the mod between AI and Pmax. So C1 in this example, so AI, the first A1, is going to be 3 minus 7 mod 3, the mod of Pmax and AI, so 7 mod 3. So it's going to be 3 minus 1, so C1 is equal to 2. And then we do the same thing for 5 with regard to Pmax. So 5 minus the mod, 7 mod 5, 7 minus 2 is going to be 5. So now our set C is going to be 2 and 5. All right, so we've defined A and B real quick, and then we use this method to define what C is. So now we're going to create a set D such that we're finding all numbers that are not in both sets. Um, So 2 is in both sets, 5 is in both sets, and now that just leaves us as 1, 3, 4, right? So d min is we're going to call that the lowest even integer in D. So the lowest even integer we have here is 4. So the idea is now we take our P max, add d min, and that's going to give us our next prime number. So 7 plus 4 is 11, or P max plus 1 is the next sequential prime number. So really this is kind of like a sieve, but I think there's something. One, it always gives you the very next prime number, and because you can you can filter out what's going to be in set A. You don't have to check every single number um, using uh, this method down here. You only have to check the odd numbers excluding 1. Um, and you don't have to check, like 6 or 7. And higher prime numbers, you don't have to go higher than basically P max plus 1 over 2. There's a reason for that. So only even prime numbers 2. So we kind of uh, don't have to worry about that too much. But so all the rest of the primes must be odd. This means that we can begin at the next sequential prime after 2. Using the Bertrand-Chebyschev theorem, this must be 3. According to the Bertrand-Chebyschev theorem, this right here, for all n in natural numbers greater than 0, there exists a prime that is such that the prime is between n and 2n. Um, but using the proof that we just did, we can show that we can narrow that down a little bit, make it a little bit more concise. Um, so we use some basic stuff from Euclid's Elements, showing that the difference between a non-number and even number will always be an odd number. Makes sense. He already proved it, and you can prove it yourself. It's pretty easy. And so that for every AI that is even, CI must be odd using the method here. If we were to use an AI that is even, then CI would always be odd. And if you add the odd number plus prime, you'll always get an even number. So we can ignore all even numbers. That's why when we defined a set A, we ignored all even numbers. That's for every CI that is odd. If CI is equal to any DI, then P max summed with that number will result in an even number, just like I just said. If you add it to the prime, you'll get an even number, therefore it can't be prime. So we can exclude all element even numbers from A and ignore all DI that are odd. Because if you add the odd number to the prime, you'll get an even number, and it's not going to be prime. So we already showed that for any AI that is odd, such this, and CI will result in an odd number. And again, this means that we can exclude any AI that is odd that is over P max plus 1 over 2. That's why we can kind of narrow down the Bertrand-Chebyschev theorem. Instead of n is what's that? N is less than p is less than 2n. We can just go to the p plus 1 over 2 plus p is must be the next prime. Uh, so the resulting conditions that we apply for A will then result in only the CI and DI such that they are even numbers. That's why we pick the lowest even number in set D. So for any CI that is even, we know that the Pmax plus CI will result in a number that is associated with AI, that the associated AI will be a factor. Yeah. So the CI is going to be equal to AI minus the mod between Pmax and AI. And that's, remember the n, where we use set it equal to 1 for some integer n. Okay, so CI plus Pmax. Let's see, it's going to be let's see how I remember how I I did all this. A yeah, okay, yeah. God dang it. It's gonna be Pmax. Yeah, Pmax is equal to this. Ci is equal to that. So we're adding these two. So we'll have AI plus NAI because the Pmax mod AI minus Pmax mod AI is going to equal to 0. And then it's just going to be AI times 1 plus n. So this means that the lowest even integer missing from that set, which is going to end up being d min, um, found using b as like the cross reference, will produce the very next prime when added to Pmax. So it's a way to always determine what the very next prime is. And it's so in what's it? Um, the Sieve of Eratosthenes, he goes through and like does each number up to the whatever number and checks what's divisible. Well, according to this method, you don't have to go through every number up to the number. Um, you find like there I think the correct term is the um, residue, mod residue, and you add that uh, the the you find the mod residue that is even, that is missing from the set, add it to your prime, and it will always give you the very next prime. And again, because of the proof that we just did earlier, we can narrow it down, uh, uh, and we can kind of modify the Bertrand-Chebyschev theorem to narrow it down. And I think this is probably already well established, um, and but it's something that my son kind of came up with, and uh, he was kind of interested in it, and a bit. He's since moved on from it, but I was curious about doing a rigorous proof for it because I mean I'm on my taking a decent amount of math, but I haven't encountered this yet, and I figure eventually I will. Um, but yeah, I thought somebody might find it kind of interesting. Hopefully, it kind of made sense.